All right, so this is the second of 3 lessons looking at inverses. Now I'll get straight into it. So I start with a fair amount of little fill in the blanks here. And my voice just cracked. So that's it. A relation is a function if it passes the vertical line test. That idea goes back to grade 10, and hopefully that sounds familiar. And basically, if you have a graph of some relationship, and you hopefully can just tell by looking at it immediately, yes or no, is it a function? If a vertical line can go through more than one point, it's not a function. Otherwise, it is a function. That should be hopefully familiar. What's probably new is this horizontal line test, which tells you if something is one-to-one. But the way it works is the exact same. If you can imagine a horizontal line going through more than one point, it is not one-to-one. Otherwise, it is one-to-one. And so if you understand the vertical line test, that tells you if something is a function. In the same way, we can use the horizontal line test to determine if something is one-to-one. But why does it matter if something is one-to-one? In fact, maybe I'll just over here, I'll just draw something. Let's make a little. For example, I'm going to draw, this is a function, this is a function, this is not a function. Okay? So let me draw one more. Let me look at these. Let me draw one more that is a function. This is a function. Okay? However, this is not one-to-one because it crosses horizontally in 3 places. This is not one-to-one. This is one-to-one. So not one-to-one, not one-to-one. This is one-to-one. But why does that matter? Well, in itself, it doesn't really matter if a function is one-to-one so much. It matters in terms of its inverses. So, determining if something is one-to-one is pretty easy to do, actually, with a tiny bit of practice. But it's easy to forget as well. So why does it matter? Well, this is why it matters. If a function is one-to-one, then its inverse will also be a function. So if some function is one-to-one, then its inverse, and remember this means the inverse, will also be a function. And the flip side is true. If something is not one-to-one, then its inverse will not be a function. And the reason that matters is once we're dealing with things that are not functions, your life generally gets more complex. Things are simpler when you're dealing with functions. If something is a function, you put one number in, you get one number out. If something is not a function, maybe you put one number in and you get 3 numbers out. And that's kind of weird. And so your life is generally simpler if you're dealing with functions. And so if a function is not one-to-one, and you start looking at its inverse will not be a function. You can still find it, you can still work with it, it just won't be a function. That's it. Looking at the graphs of how a function and its inverse compare, they are reflections of each other, but they're not reflections on the x-axis or the y-axis. They're reflections on the line y equals x. And in terms of coordinates, if x comma y is some point on a function, then on the inverse, there must be a point on the graph that goes through y comma x. The x and y coordinates are swapped around. So a lot of things mentioned here. These are explored in the group problems. Let's kind of use them in these next few examples here. All right, so I have a graph of f of x, 3x plus 2. And let me just kind of label it up here as well. So this line we see is f of x. It's as an equation, it's 3x plus 2. Okay, so what I want to do for each of these is find the graph of the inverse and state the domain and range of each. So I want to find the graph of the inverse of what I have right here. I have a few choices. One choice is to look at find the equation of the inverse. And so it's not wrong. So if I want to find the equation of the inverse, I can write this as y equals 3x plus 2. Since I want my equation of the inverse to have x as the input, I'm going to swap around x and y. And I'm going to solve for y. So add 2 to both sides. Divide by 3. Y equals x plus 2 over 3, which means the inverse of f I can write as x plus 2 over 3. So what does that look like? Well, I can figure it out, but it's not terribly helpful. In this case, the inverse equation, I could also write it like this, same as x over 3 plus 2 over 3. So I can see it is a linear equation. I can see its slope and its y-intercept, but like I said, it's not terribly helpful. So nothing I did was wrong, hence I did it. But for what I'm trying to figure out in the question, it's not terribly helpful. What's probably more helpful is remembering that I said that all inverses, if you think of the graphs, can be thought of as a reflection on the line y equals x. And that's what I'm drawing right now. This dashed line is the line of y equals x. And if I can imagine placing a mirror along that line, how that would create a new image, if I can visualize that, I can visualize the graph of the inverse without using the equation. Even better though, this last point I mentioned right here. If we know a point on one function, then we know a point on its inverse. All I got to do is swap the x and y coordinates around. So everything I've done is correct, but it's this last thing that's going to be the most useful for me for this particular question. I'm going to pick a point. How about right there? What are the coordinates of that point? 0, 2. So I know the inverse must go through 2, 0. There we go. I think that was easier than anything else I've done. I also know the inverse is going to be a line because it's the reflection of a line. So my inverse is going to be a different line. So all I really need is one more point. Maybe I'll look at this point right here. This point right here is at -2, -4. So I know with certainty my inverse must go through -4, -2, which is right here. And that's all I need to make a line. I can pick some other points, but that's good enough. So I'll grab my ruler, draw a line, and there's my inverse. And I'll label it as y equals the inverse of f. I could write down the actual equation, but I don't really care. There we go. So notice this work I did with the algebraic work wasn't useless at all. It wasn't terribly hard, but it wasn't, I don't think, as useful as this other key point that if you know the graph of a function, its inverse, you can always visualize by swapping around the inputs and outputs, the x and y's. That's it. If I look at both of these graphs, they both have the exact same domain and range. They're all real numbers. And so I'm just going to write it down here. So the domain of f of x is all real numbers. And the range of f of x is all real numbers. Oops, keep these color-coded the same way. And same thing for the inverse. Because they're both linear functions that go on forever, up and down, left and right. So not much more to really see from that. It's all the same. All right, so let's look at g of x. Let me label this here. So this is g of x, a quadratic function. I can see right away by looking at it, g of x is not one-to-one. It fails the horizontal line test. A horizontal line right here goes through 2 points, which just means the inverse, whenever I graph it, is not going to be a function. The inverse is going to fail the vertical line test. And again, if I want, I can find the equation of the inverse, and I will, but it may not be that helpful. But that's it. It's also not that hard in this case. So to find the inverse, I'm going to write this as y equals x squared minus 4. Swap around x and y. Solve for y. So remember, when I square root both sides, I should either get a plus or minus, which means my inverse, that I'm going to draw in red again, is going to be 2 equations at the same time, which is kind of weird. It's plus and minus root x plus 4. And later on in the course, like the next chapter, when we start looking at radical functions in detail, which is what this, root x plus 4 is a radical function, then we can use the equation a bit better to visualize it. But I can see, just from my algebraic work, that my inverse is not a function. I put one number in, and I get potentially two numbers out, depending on what I pick for x, a positive and a minus of that root. And so that's it. What's the graph look like? Again, I'm going to draw my reflection line of y equals x, but again, it's actually not that helpful because it's kind of hard to visualize a mirror placed right there. What I think is helpful is to pick a point and swap the x and y coordinates around. So this point right here is at 0, -4. So I know the inverse must go through -4, 0. And I will pick 2 more points. I'll pick these points here. And so, for example, on the left, that point is at -2, 0. Now it's going to be at 0, -2. This point right here is at 2, 0. It's not going to be 0, 2. Whoa. And that's really all I need. Personally, if you're looking at this and you're not really sure what to do next, just pick more points. Pick these points. You'll see they match up right here. And the more points you pick, the harder it is to miss something. That's it. I can see what this looks like. It's a parabola kind of reflected, kind of sideways. And notice what I'm sketching out here fails a vertical line test. That's okay. We knew it would. This is my inverse. It's not a function. Right? When x is 0, the output is either 2 or -2. Both. That's kind of weird. You put one number in, you get 2 numbers out, but that's what happens quite often when we deal with things that are not functions. Domain and range. I can see a few more things here. Notice if I look at g of x, the one in blue, the domain is all real numbers. Notice if I look at my inverse, that's my range. The range is all real numbers. And we notice that from the last lesson that these are always connected. Looking back at function g, the range is everything greater than -4. And notice that's the exact same as the domain of my inverse. And so that idea about how the domain and range are connected to one another, we're dealing with inverses, we saw last day. And again, so obviously it'll continue. So the last example before a final problem doesn't have any equations, it just has a graph. Okay, so here's h of x. And just by looking at it, I can see h of x is not a function. Sorry, take that back. H of x is a function, it's not 1 to 1. So I know the inverse will not be a function. And so I'll draw my dashed line here. But I don't even have an equation to work with so much here. So how do I find the graph of the inverse? Do the same thing I did before. Pick these points, swap around the coordinates, and then essentially connect the dots. And so if I start with this point right here, the coordinates of that are -5, 4. So now it's going to be at 4, -5. Looking at this point right here, the coordinates are at -1, 4. So now it's going to be at 4, -1. At this point, I'm going to connect these dots right now. I know they must be a vertical line right there because these 2 points were connected to one another. So these 2 points must be connected to one another. Again, when we reflect something, the image doesn't change. It's congruent. It's just kind of flipped around or whatnot. This point here is at 1, -2. So the reflection image is going to be at -2, 1. And I'll draw a line connecting them. Just 1 point left. This endpoint here is at 5, 2. So now it's going to be at 2, 5. And there's my inverse. And so domain and range. Notice again, I'll see how these connect to one another. For h of x, the domain is from -5 up to +5. And notice that's the range of my inverse, from -5 to +5. And because once you know one, you know the other. So range of my function h is from -2 to 4. And notice I don't even have to look. I'll just copy -2x to 4, and now I'll confirm that the domain of the inverse really is from -2 all the way up to 4. And it is. All right. So the last problem connects to the last part on inverses. So this last problem here is really sort of a bridge to the last lesson we'll have on inverses. So, sorry, I'm just...
What time does the school actually get over?
Oh, sorry, I'm just recording something right now.
No, what time does the school actually get over?
2:55.
Oh, not 2:45?
Yeah, not a problem. Oh, guest appearance by Miss B. So with that said, what's this last question? I have f of x. And f of x, notice, is x squared, but then I have this little comma. X squared, or x is less than or equal to 0. So this is what we call a restriction. I have a restriction on x squared. And so f of x is x squared, but only dealing with x that's less than or equal to 0, which are negative values. So that's my function. So what do I want to do? Well, I want to graph f of x as well as the inverse of f of x on the same grid. Okay, so let's start with f of x. I want to graph x squared, but only where x is less than or equal to 0. Well, let's first just focus on x squared. X squared goes through 0, 0, 1, 1, 2, 4, 3, 9, and x squared is symmetrical. So if I draw this, this is a wonderful graph of x squared. But I don't want x squared. I want x squared where x is only less than or equal to 0. So I only want to keep parts of the graph where x is essentially negative or 0, which means I want to erase all of this right here. Because this part I'm highlighting in blue, that whole region is where x is positive. So I want to literally grab my eraser, and I'm going to erase this. There we go. So this is the graph of x squared where x is or x is less than or equal to 0. Or, as I called it, f of x. However, I will put these other little dots here back, and I'll just kind of draw a little dashed line to show that this wasn't useless, but that's not what I wanted. In fact, I'm going to draw it even lighter. I don't want us to, it's getting a bit too dark. All right, so there is f of x. So what's the inverse of f of x? Well, I would just pick these points and swap the coordinates around. And I'll draw this in red. So starting with the vertex, 0, 0, swapped around, doesn't change. It's invariant. Next, this point right here is at negative 1, 1. That means its inverse must be at 1, negative 1, right here. Next, this point here is at negative 2, 4. Now it's going to be at 4, negative 2. And lastly, right here, this was at negative 3, 9. Now it's at 9, negative 3. And so what does this look like? It looks like just this. And that's it. Just this section I've drawn right here. So this is the inverse of f of x. That said, I'm done. But I would like us to notice a few more things before I wrap up. First of all, let's look at the equation. Let me go back to the equation of f of x. F of x had an equation of x squared. What if we found the inverse of this? Ignoring the restriction for a moment. The inverse, I could find quite easily. Right, is like this. Swap x and y around. Square root both sides. So you have plus or minus the square root of x equals y. And so we could say the inverse of f is plus or minus root x. However, what I have right here doesn't have a restriction. And so if there was no restriction, if that restriction wasn't right there, then my inverse would, look like this. It would also have a top half. So if f of x did not have a restriction, if f of x was just x squared, then my inverse as an equation would be plus or minus the square root of x, and my graph would be both the top and the bottom. But again, that was not the case. And so my equation is actually just the negative version of it. However, this part right here is really what we'll be focusing on for the last lesson, the sort of connection between the algebraic and everything else. Because honestly, I did this quite quickly. However, everything is connected, and so anytime we're focusing on something purely visually, doesn't mean we're wrong, but I want to make sure we see how all these are connected to one another. Okay, however, I will say, if this question kind of made sense until I did this last little part here, then just focus on the graph. All right, because again, what I'm highlighting in yellow right here, that was the inverse to f of x. Just that part I've highlighted in yellow. And with that said, I'm going to stop this, and thank you for watching.